Example number 2, we have a graphing an exponential function. In this example, we are supposed to use transformations. So if you notice, here we have 3 raised to power x is the basic family of the function. From there, we have 3 raised to power x minus 2. So what is happening really is x is changing to x minus 2. So that means graph moves right by 2 units. And from there, we are having 3 raised to power x minus 2 plus 4. That means y is changing to y plus 4, meaning moves up by 4 units. So you can use the calculator for this also. Say I write, you can check, let's say 3 raised to power x. That's the basic exponential graph which we are saying is passed through 0, 1 point. It is an increasing graph because the base is more than 1. It's an exponential increasing graph which goes to 0 as x approaches to negative infinity, and it goes to infinity as x approaches to positive infinity. Now I'm going to go to the next y and write 3 raised to power x minus 2. And you're going to see that the same graph, it's like if you could pick it up and move right by how many units? 2 units, because subtracting 2 goes in the opposite side. So graph moves right by 2 units. Then you go down in y3, you write 3 raised to power x minus 2 plus 4. What is that supposed to do? According to our analysis, it is supposed to move the graph up. So that red graph is finally moved up by 4 units. And actually you can press second and table to look the values of each of these functions. So at 0 it is 1, and then it goes different point, and at 4.11. So this is your graph, the final. So for the final graph, you can clear, I just want to see the transformations, but basically what you have to answer is only this black graph. A graph passing through 0, 4, and as x approaches to negative infinity, the graph approaches to 4, and as x approaches to infinity, the graph approaches to infinity again. Next, I want to define a special number which is called e. It's an exponential number. E is a universal constant. It's like pi, right? Pi is a special number. E is also an irrational number. So its definition basically comes from calculus, so we are not going into details of it. As x approaches to infinity, this expression approaches to a constant value which we call e. E is called an exponential number. E's value is roughly taken to be 2.71. So on your calculator, if you see, E is written here in the second form of the button ln. So natural log. So if you press second this, you will get E here. And if you write E raised to power 1, that will just get you E's value, that is 2.71. Or you can find E raised to power, say 2, E square, and so on. Okay. So E is a special number. So what example number 3 is telling you is to graph E raised to power x. So if you notice, E raised to power s, we said E is approximately 2.71, right? So we graphed 2 raised to power x. So we said it was something like this. This was 2 raised to power x. Then we said if we can graph 3 raised to power x, it will steep faster because the base is larger. So we can say that if we have the graph of e raised to power x, it would be passing somewhere between this 2 raised to power x branch and 3 raised to power x branch. Why? Because this is e raised to power x, and e, which is 2.71, lies between 2 and 3. So its graph is going to lie between these two branches of the exponential function. And if you want to use calculator, you can simply in y, clear what you have before. In y1, you can write second, press natural log, that will get you e, write the variable x, enter, graph. So that is your e raised to power x. And I actually want to show you its position. If we have 2 raised to power x, that would be the red graph, and 3 raised to power x, that would be the black graph. You will see that blue curve lies somewhere between red and the black curve. Okay, so the graph of e raised to power x is also an exponential function graph. It looks like that. You should know how to evaluate e's values, e's power values. You can simply use the calculator. For example, number 4, e square. We just found e square, so that is 7.39 approximately. If we have to find e raised to power negative 3, we are going to say second natural log. That's going to get you e raised to power negative 3. We have 0.49, so 7 rounding off 50. We can say second e, second square root of 7. That will be 14.09. The last one is e raised to power pi. Second e, pi is here. Second pi, this number is 23.14 approximately. So using calculator, you can find. So, oh, they are asking you to write 4 decimal numbers. So you can do that. E the power negative 3 was rounding off to this, and this one will be 73890. This would be this, and to the 4 decimal, this would be this. Next, we have application problem of exponential functions. The first important application is about compound interest. Suppose we deposit P dollars in principal is invested or borrowed at an annual interest rate of R for T years. Then simple interest, if you want to calculate simple interest, I would be equal to PRT, where P is principal, R is the rate per year, and T is the time in years. If we are talking about in the compound interest problem, then the final future amount A is equal to P times 1 plus R by N raised to power NT. N is the compounding number of periods per year. T is the number of years we are having. And the last, if you're talking about continuous compounding, then the amount future value is equal to P times e raised to power RT. R is the rate of interest per year. T is number of years the money is kept in the account, and P is the principal amount, how much you invest. Let's do an example to see how this formula works. Suppose $5,000 is invested, pays 6.5% per year under the following compounding options. The first compounding option is given compounding annually. Now remember, our formula is A is equal to principal times 1 plus R divided by N raised to power N T. Now in part A, when it is compounding annually, N, number of compoundings per year, is just 1. From here we have principal is 5,000, interest rate is 6.5%. In the decimal, that is written as 0.065, and T is given to be 10 years. So principal is 5,000, N is 1, T is 10, and R is 0.065. We always have to work R as a decimal number. So amount will be equal to 5,000 times 1 plus 0.065 divided by 1 raised to the power 1 times 10. So 5,000 times 1 plus 0.65 raised to power 10. I can use calculator to calculate that. Times 1.065 raised to the power 10. That one is 9,385.69. What happens if we are compounding quarterly? In part B, compounding quarterly means n is 4. So amount, the formula is same, principal is same, interest rate is same. So this 5,000 plus 1.065 divided by 4 now, raised to power 4 times 10, because 4 is the number of compounding periods. So we can calculate 0.065 divided by 4 plus 1 raised to the power 40 times 5,000. So we have 9,527.79. So you see, if we do compounding, same amount of money, same interest rate, but if it's compounding quarterly, we are getting more money out at the end of the same period, 10 years. What happens if it is compounded monthly? If it is compounded monthly, how many months are in a year? N would be 12. So amount will be 5,000 times 1 plus 0.065 divided by 12 raised to power 12 times 10. So you can use calculator to calculate that. Next we have compounded daily. How many days are in a year? 365. So amount would be 5,000 times 1 plus 0.065 divided by 365 raised to power 365 times 10. You can use calculate to calculate that. And the last one, compounded continuously. If it is compounded continuously, the formula is different. It is principal times e raised to power r times t. Principal is 5,000 times e raised to power 0.065 times 10. So you can use calculator to calculate all of these numbers. The last one here is 5,000 times e raised to power 0.065 times 10. So that is 9,577.70. So similarly, I calculated all these numbers using the calculators. So it depends, right? When it is monthly, when it is daily, when it is continuously, with the same principal rate, same timing, same interest rate, the final answer keep on changing. So that's how we need to figure out which case is the best for us. So this was quarterly and this was annual.